Okay, so in the last class what we have discussed is how from Fourier, last few class probably I should say, how from Fourier series towards Fourier transform. So that means we have an energy signal, from there means we have a power signal, from there we get Fourier series. That is something we have already explored. And then if instead of energy means power signal, we have a non-periodic signal, that is energy signal, which is time bounded. For that, how do we actually evaluate the frequency components? So what we have seen that whenever means we have put a trick over there. So instead of doing the analysis completely in a new fashion, we have actually borrowed the idea from Fourier series. So what we did, we have taken a time period which is bigger than the existence of the signal. So that means if the signal is defined from, let's say, A to B, we have taken the time period as a time period which includes that entire thing, and then we started repeating this signal, the entire signal. So what was happening, the targeted signal was repeated over that period t, if I say this is t, and then we said that immediately if I start repeating it up to time plus infinity and minus infinity, so immediately it becomes a again power signal, okay, and it's a periodic signal. So we can get Fourier series accordingly, and then we started stretching this t to infinity. So immediately we could see that we were getting a Fourier transform case. So we have given interpretation of Fourier transform, what exactly it means. So if for a signal gt we get a Fourier transform which is gf, what's the meaning of that? We have said that at any frequency f, the value of gf is not actually the spectrum component as it was for our discrete Fourier series case. So we have told that that generally gives me 0, but if I just multiply gf with some del f, okay, then within this del f how much frequency component is there, that can be actually evaluated. So that is why gf is called as spectral density, because gf del f is almost similar to that dn, and then gf del f divided by del f is actually giving me gf. Okay, so that means dn by del f. So this is actually the spectrum divided by the frequency part, so it becomes spectral density. So this is something we have already discussed. Okay, so we have given some interpretation about that gf, what does that mean. Now what we wish to do is now from here to measurement. We have already defined that energy or power is kind of measurement for us. Okay, that's almost like in vector also we get the distance of a vector, which is measurement. We have shown that similarly if we just integrate either g square t or mod gt square, we get energy. Okay, and correspondingly if it is a power signal, then we can evaluate power just dividing by time and stretching the time up to infinity. Okay, so we'll now try to get into the energy or power of a particular signal. So our target is similar to what we have done. We have also evaluated the power of a periodic signal, right? That's something we have already talked about, and we have given the equivalence means power calculation theorem, which is called Parseval's power theorem. Okay, so similar theorem will be trying to derive for a time limited signal or a energy signal. So let's try to see. If I have a signal gt, okay, which is time bounded. Okay, so the signal can be anything. I am just taking this signal. It might be of any nature. So it might be of this nature, defined between some finite amount of time. Okay, so if I just take that gt, I wish to now evaluate the energy of this signal. Okay, so you might be saying, okay, it's very easy. We already have defined this particular thing. So it's all about integrating mod gt square dt, right? Or if it is a real signal, then it's just integrating g square t dt, right? So this is our, means this happens when the signal is real, This happens when the signal is complex, right? Or we can write that mod gt square as gt g star t dt, right? So what we'll do, we'll probably take the more generic definition, which is the complex signal definition, because complex signal already takes the real part, right? If it is real, then g star t will be gt, and immediately we get g square t, right? So for that case, I wish to evaluate this. You might be asking, so this is my energy. You might be asking, this is by definition, already we have defined this. We have also, from the definition of Fourier series and Fourier transform, we have already defined that this should be the energy, right? So this is something was already derived. So what we are targeting now, like what we have done in Parseval theorem for Fourier series, we wish to also define energy from the frequency spectrum. This is what we are seeing from the time. Okay, so gt has equivalent Fourier transform. Let's say that is gf, because gt is a time limited signal, so it must have a corresponding Fourier transform which is well defined. Okay, as long as gt has some property that we have discussed already. So gf is already defined. So I want to see in the frequency domain, can we evaluate the power or energy similarly. So for this signal, because it's a time limited, so it should be an energy signal, so we'll be interested in energy. So let's try to see if we can define that thing. So what we can do is something like this. We have already talked about inverse Fourier transform. Okay, so in that inverse Fourier transform, we have said gt is represented, as long as gf is known, it's minus infinity plus infinity gf e to the power plus j 2 pi ft df, right? So that's the theorem we have proven already. That's the inverse Fourier transform. So this g star t will be replacing by this. Okay, so it will be one integration over f gf. Of course, because we have to take complex conjugate, because this is gt, we need to get g star t. So g star t will be g star f, and it will be, there will be a minus sign over here. So I can replace it by that. So it will be g star f e to the power minus j 2 pi ft df, right? No problem in that. Whatever we have derived so far, we are just using those things. So because we want to take it to frequency domain, that is why we are applying this inverse Fourier transform. So the time domain signal, I am actually representing it through inverse Fourier transform to frequency domain signal. But so far I have only succeeded in replacing one of them. Of course the dt should be still there. So this is where we have replaced g star t. Okay, we have to see what happens to this gt. Now let's see this integration limit. Okay, so they are not dependent on each other, so I can always flip these two integration. So I can take the frequency integration outside. So whatever terms which involve only frequency, I can take that outside. So g square f will be, g star f will be there. Inside the time integration should be there, where gt is already there, e to the power minus j 2 pi ft. This is also a thing which is dependent on time, so I cannot take that outside that integration. So dt integration is being done first, and then df, right? No problem, I have just rearranged it, and I am allowed to do that rearranging because the limits are not dependent on each other. Okay, and whichever functions are dependent on both f and t, I have not taken them out. So I have done all the things correctly. So now let's see what happens over here. Can you identify this thing? So it is actually the Fourier transform of gt. We have already defined that. Okay, so and we have derived that. So this is Fourier transform of gt, therefore this must be gf. So that's gf df. So basically what has happened, we have started the definition of energy from time domain, and eventually we could get into frequency domain of the same energy. So what happens in frequency domain? It is nothing but mod gf square df, right? So basically in frequency domain, now you can see also what's happening. My GF might be a complex term. We have seen that already. It might have a phase component, it might have an amplitude component. What here we are doing, because we are measuring a real quantity Eg, so basically we are taking, the formula says that I must take the modulus of GF, which is real again, and square of that I integrate over the entire frequency domain. Whatever I get back, that's actually energy. So in the frequency domain, whatever pattern I am getting, this mod GF square, if I plot, okay, so suppose this is frequency and I am plotting this, I have a corresponding GT, let's say that GT looks like this, and I am plotting mod GF square, which will be eventually looking like this. Okay. So you will later on see if GT is this box function, it becomes sinc square. Okay. So sin x by x square of that. Okay, so it looks like this. So if my GT is this, I plot, this is actually mod GF square. This I call it as energy spectral density, or ESD. Why it is called so? Because first of all, if you integrate it from minus infinity to plus infinity, that means all the frequency component you are actually trying to evaluate something which is mod GF square. I still don't know what that is. Okay. So if I integrate that, I get the overall energy. Good. And if I suppose try to see what are the frequency component it has, or a measurable quantity of some frequency component it has. If I try to see that, what I will be doing, I will be passing this through a band pass filter, very narrow band pass filter of, let's say, a band pass filter centered around Fc and with this one as delta F. So the filter, if you correctly plot that, it will, the transfer function will look like this. So it will have, in the plus Fc there will be a flat band where it will pass every frequency, and minus Fc also because of the symmetric nature in Fourier transform. So it will have something. Okay. So if I pass this, what will happen? I will have a multiplication of these two, right? So immediately what I will get, only at that frequency this mod GF square will exist, because it will just pass, and in all other frequency it will be 0. And then if I just try to see that, suppose the band is over here, let's say. So what I will get, I will just get the same almost similar pattern over here. And if I just now integrate, what I should expect now, that in those frequency band how much power it has. Okay. So in that del F, because the overall power is, if I integrate it fully, now I am passing it through filter, filter will be passing only on that band whatever it has exactly as it is. So if I now, after passing through filter, if I now wish to calculate the energy, that must be those frequency component energy, because those are only getting passed through this filter. So that frequency component energy is becoming just the integration of this mod GF square over that frequency band. So this is the reason why this is called energy spectral density, because what is happening, for a particular frequency band how much energy is there, that's being characterized by this mod GF square. Okay. If you just target a particular frequency, at that frequency, just if you take only that frequency, you won't get any energy, because if you integrate it will be 0, right? Because I don't have any space to integrate, it's just a on a point I am trying to do integration, so that will be 0, because there del F is 0. If I allow some del F, I will be immediately getting some amount of energy, and that energy characterizes that at that frequency, if del F is sufficiently small, at that frequency, around that, how much energy per unit band it has, because it is integration of that. That means if this del F is sufficiently small, it will be almost flat, right? And then the value of mod GF square into del F, because it's almost flat, it can be approximated as flat. So if this is drawn like this, and I have chosen a very small this one, so you can see the top is almost flat if I make my del f tending to 0. So then the overall energy will be this mod gf square, almost similar concept, into del f. Of course, because it's two sided, so it should be 2 into that, okay, because I will be getting same thing in both the sides. Okay, so if I just ignore this 2, because this will be always there, whichever band I choose, it will be always there. So what is happening if I divide this by del f? Okay, so I get to see that per unit band, okay, because I am dividing it by frequency, this mod gf square is actually giving me the energy per unit band. So that is why it's called energy spectral density, because mod gf square gives me an idea that at any frequency I choose per unit band how much energy is being there in that signal. So it actually characterizes the overall signal, because we have told that this energy is a measurement. So it characterizes the overall signal. It just says every frequency term how much energy, or means spectral density. I should not say spectrum, it should be spectral density, how much spectral density it has at that targeted frequency. Okay, because it characterizes that, so that is another way of characterizing the whole signal. Okay, so that's the importance or significance of this. So we have now got some measurement or measurable quantity in the frequency domain as well, because we have now defined two separate domain for representing a signal. One is the time domain, another one is the frequency domain. Now we have got a frequency domain representation of measurable quantity, which is energy, okay, or energy spectral density. That's something we have got. Now we will introduce another thing. Okay, so that is that if I have a signal GT, let's say this is GT, how do I get my energy spectral density? The technique is very simple. First, do a Fourier transform. Okay, so whenever I do a Fourier transform, I will be getting corresponding mod gf square, right? Means first I will be getting gf, and then from that gf I can calculate the mod gf square. So that becomes my energy spectral density. This is one way of evaluating energy spectral density. But I would say most of the time the helpful one is not this one. Okay, so we will try to see the what is the other method to actually evaluate energy spectral density. So for that we will try to define a particular term which is called time autocorrelation function. What is time autocorrelation function? So suppose I have a time bounded signal GT. It might be like this, it might be anything but bounded in time. Okay, so this GT, if I multiply with a either advanced or delayed version of that same signal, so it might be t plus tau. Let's say it's advanced by tau amount of time, and if I integrate this over the entire time. Okay, so I take a signal, so it might be this signal, and then probably this means actually it will be delayed. Okay, so it will be shifted backwards. So if I just shift it by this amount, so this is actually tau, and then I'll multiply these two. So this is GT and this is GT plus tau. Okay, if I multiply these two signals and start integrating it, we are saying this is, we are just defining it. Okay, right now probably you won't appreciate why we are defining this, but later on you will see that this has a big implication in communication or signal processing. So we are defining this as phi g tau. Of course we are integrating it over t, so the tau will remain. So it's a function of tau. For different values of tau, this integration will be different. You can see already. If I put a tau which is sufficiently large than this particular duration of this signal, then it will become 0. Whereas here it is not 0, it has a overlapping part. Okay. So it depends on, of course, this will be dependent on tau, whatever tau I choose. So it is a function of tau. Okay. So this is our time autocorrelation function. First of all, let's see some property of it. We'll later on link this to something of our interest, and then you'll appreciate why we are defining this. But let us first try to characterize this particular signal. So first thing we wish to prove is that it is a event symmetric function. So let's say my definition was this. Okay. Now let us substitute t plus tau as z. Okay. So what will happen to t? That should be z minus tau, right? And dt will be, tau is a constant, so dt will be, for this integration tau is a constant, so dt will be dz. So this phi g tau should be minus infinity plus infinity gt g. Okay, so now we have to do the substitution. So t will become g z minus tau, and t plus tau will become gz, and this become dz, right? So again, z is just a dummy variable, I can replace that as t. So it will become minus infinity plus infinity gt gt minus tau dt. Just think about this and this definition. What is happening if this is phi g tau? Okay, this is actually phi g minus tau by this definition, because if tau is replaced by minus tau, this automatically becomes, so if I just replace tau by minus tau, this becomes phi g minus tau, which is exactly equivalent to this particular thing. But this is equal to this, therefore this must be equal to this. So I can see my phi g tau is a event symmetric function, because the negative of, means tau, if I replace by minus tau, I get the same value. So it's a event symmetric function, right? Okay. Next, the most important thing that I will be doing. So now what I wish to do is, I wish to take the Fourier transform of this one. It will be very clear after some time that why I am doing this. Okay. So right now I am just doing it. Okay. So I wish to take the Fourier transform of this particular signal, right, phi g tau. Of course, when I am saying that I am taking a Fourier transform, my Fourier transform is actually transforming it from tau domain to some other domain. Okay, let's call that as f domain. So it's no longer the t domain, because here the means independent variable is tau, so Fourier transform should be on tau. So let us put that Fourier transform. Fourier transform means I have to put the function, so which is nothing but minus infinity plus infinity gt plus tau dt, right? So this is my whole signal that has to be Fourier transform, okay, into e to the power minus j 2 pi f tau, because the variable is now tau d tau, integration minus infinity plus infinity. So that is the Fourier transform, right? So let's now try to see if we can evaluate this. Again, I'll do a means change of this integration, because they are not dependent on each other, the limits are not dependent. So I can keep the t integration out and put the tau integration inside. So whichever is free of tau, that will be going out, so gt goes out. So I have minus infinity plus infinity g t plus tau e to the power minus j 2 pi f tau d tau, right? So this is something which is there inside. Okay. Now I'll just do again same trick, t plus tau I'll replace as some y, let's say. Okay. So immediately what do we get? minus infinity to plus infinity gt, now minus infinity to plus infinity, this is becoming my y, so gy. Okay. Now tau is a variable, so tau must be, and for this integration t is a constant because this integration is over tau. Okay. So t is actually a constant for that integration. So I should not bother about t, so tau becomes y minus t, right. So this becomes e to the power minus j 2 pi f y into e to the power plus j 2 pi f t, right. Okay, I have just replaced tau by y minus t. So y, that minus is there, and minus t becomes plus. Okay, and dt, right. So this is that integration. Now let's see, for this particular integration inside, this is a constant term. Okay, because it has nothing dependent on tau, so I can take that out. Right. What I have is, and of course I should also say d tau, because t is constant, so that should be replaced by dy, and the integration because it's minus infinity plus infinity, that's not changing. So now I have got gy e to the power minus j 2 pi fy dy minus infinity plus infinity dt outside. What's this? That's actually Fourier transform of g. If I know already the Fourier transform, suppose gt or any variable gy whatever it is, because transform takes it to another domain. So this is gf, suppose. So that must be, because y is just a dummy variable, I can put y as, treat y as t. So I'll be getting gf over here, right. So I can immediately write this as minus infinity plus infinity gt e to the power minus j 2 pi f t. This becomes gf dt. Oh, there should be, sorry, this was plus, this term was plus, that mistakenly I have written minus. Fine. Now what's happening? gf is no longer a function of t, I can take that out, gf goes out. What I am left with, gt e to the power plus j 2 pi f t dt, right. If this was minus, then I could have got a Fourier transform, right. So I can forcefully put a minus over here, and then I have to put minus f over here, right. So immediately what happens, this is the Fourier transform of whatever is there inside, so that should be g minus f. So I can write gf into g minus f, right. We have also proven that Fourier transform is even symmetric. So g minus f is nothing but the complex conjugate of gf. So g minus f is actually g star f. I can put that as gf into g star f. Now you can see the beauty of it. So what has happened, I have started with autocorrelation function. This is why I defined autocorrelation function, because I knew that autocorrelation function, if I take Fourier transform, I'll be getting back my energy spectral density. So this is, and that is why we were telling that there is another way of defining energy spectral density. It is just, you take first, instead of taking directly Fourier transform, you'll see why that is required. You take first, you take the signal, you take the autocorrelation of that, okay, and then you do Fourier transform, and immediately you get back your autocorrelation function. Later on you will see this is actually the famous Wiener-Khinchin relationship. Of course we have done that only for time autocorrelation. This has, Wiener-Khinchin theorem has higher implication. When we study about random process, you will see that it gets also related to that. Okay, so this is, but right now we should be satisfied with that. If you just take a signal, single signal, don't think about randomness in it, a single defined signal. If I take a time autocorrelation, okay, and do a Fourier transform on that, I get back my energy spectral density, the way we have defined energy spectral density. Earlier we have already defined what is energy spectral density. So now with time autocorrelation function we are getting back the energy spectral density. What we'll do next is, this was done for a energy signal. We'll do the same thing for power signal, and then we'll try to interpret why this is so much important. Okay, why we have to take this detour path, where we have to evaluate the time autocorrelation function and then try to take Fourier transform. We'll try to give a simple example where you'll see that Fourier transform is not good enough. Just directly taking Fourier transform might not be good enough.